Okay, now we consider another example using the dominated convergence theorem. So consider that we have a scalar a, and then consider this integral. The question is, can we show that this integral converges to 0 as k goes to infinity? Okay, so this is what we want to prove. Okay, as you can see, we can definitely consider this integrand as the function fk of x and show that this one goes to 0. Okay, but there are many cases involved in this function fk, then we want to make this as simple as possible. So to do that, let's first do a change of variable. Because we have the kx appear several times, so let's call the k times x as the variable u. So consider u as k times x. For every fixed k, we consider u equals to kx. And then by doing the change of variable, we can see that the integral of the k square x e negative k square x square over 1 plus x squared. We just need to make sure that the k goes with the kx goes together. So it's a to infinity, and move one of these k's to the x. So we have the kx e negative kx squared, and apparently on the denominator, I will have 1 plus kx squared divided by k squared. And then, as I said, I will put 1k together with this x. And since we defined the u to be kx, this is just a u e to the negative u squared, and then 1 plus u squared over k squared, and then du. But since the x is from a to infinity, so the u is from ka to positive infinity. But I can rewrite that as from 0 to positive infinity, ue negative u squared, 1 plus u squared k squared, and I put a characteristic function for the interval. Okay, du. And now I'm going to define this whole integral to be the fk of u. Okay, I can change the u to back to x to change the symbol, but this is our integrand. Okay, so now we can show two things. Apparently, when k goes to infinity, this one goes to 0 pointwise, right? And actually, this one is bounded because we can see that the fku is equal to u e negative u squared over 1 plus u squared over k squared. So I know that this one, the denominator is greater than or equal to 1. So that numerator is less than or equal to u times e negative u squared. Okay, and this one is bounded. Actually, you know that e negative u squared is is part of the the Gaussian, the probability density function of the Gaussian, and the u is linear. But we know that this one when u goes to infinity, this one goes to 0 very quickly, and it will dominate the u. And when u goes to 0, we know that this u, this one whole thing will go to 0 because this part will go to 1, and this part goes to 0. So it's bounded, and actually it's integral, and we're going to use that fact soon later. But anyway, right now this the fk of u is equal to that. Actually, not just like fku, it's just itself is bounded by that, and fku is even multiplying these two sides by this characteristic function, and that is bounded by 1, right? and it's going to 0. So this is a bounded thing here, and this is something going to 0. So the whole thing is just going to 0. So my fk, so the fk of u is approaching to 0 everywhere. On this interval, and also the fk of u, which actually is already non-negative, and that is bounded by the ue negative u square, and this one is integrable, right? This one is integrable. We actually compute the integral of this right-hand side, because the integral of this u negative u square dx, you can just take the integral of that. You can easily show that this is just a 1/2 e negative u square times u square from 0 to positive infinity, and this is actually bounded, right? Okay, so it's integrable function. Now, okay, we consider the next corollary. Okay, we have the following corollary. Suppose we have fk that is integrable for each k, and suppose the sum of this the series of these integrals is bounded, then the sum converges almost everywhere on E. Okay. And then we can also define the f to be the series for each point. Then we can show that f is also integrable, and the integral of f is actually the series of such integrals. Okay. Now, let's see how to prove this. First of all, because this series is non-negative, and we're taking the sum of this, so you know that this we can by the Beppo-Levy's theorem, we can show that this limit is equal to the integral of the series of the function. So we know that this integral of the sum k from 1 to positive infinity fk, this is equal to the sum of the integral fk, and this is finite. And this means that this function here is integrable. So the sum of this fk is integrable. Okay, it is integrable means that it's finite almost everywhere. So it's finite almost everywhere on E. Okay, and it's finite almost everywhere on E. That means for almost every x on the E, the infinite sum here is convergent, is finite, is convergent. So that means the fx defined in this way is finite almost everywhere. All right, and then because of this, we can also consider the integral of the partial sum. So let gk be defined as the partial sum of f. And then we can see that the gk converge to f almost everywhere, right? And at the same time, we just, if we want to show the integral of f, we just need to check the integral of gk and see if gk is uniformly bounded by some integrable function. So consider the gk. The gk, or actually the absolute value of gk, is equal to the absolute value of this partial sum, and apparently that is less than or equal to this by triangle inequality, and this is less than or equal to the sum, the complete sum, or infinite sum. But this one is integrable. So that means my gk, the sequence gk, is dominated by this integrable function. And this gk goes to f almost everywhere. And by the dominated convergence theorem, we can show that the integral of gk converges to the integral of f. So by the dominated convergence theorem, the integral of gk, which is the integral of the partial sum, will converge to the integral of f as k goes to positive infinity. Okay, and now let's see what this actually means. That means the left-hand side is the limit of k going to positive infinity, and this integral of this partial sum. But this one, we show that this one is equal to the integral of f. But the left-hand side is actually equal to the limit where I can pull out the sum, because it's a finite sum. I can always pull out of the integral of fk, and then the limit of k applies to the upper bound of the sum. So this is just the sum of j to positive infinity of f. So it should be fj. Okay, it should be this. But I just change the variable j to k, then we'll get the claimed equality. Okay. So that's why how we show that the partial sum, a limit of the partial sum of the integral is actually equal to the integral of the sum. Okay. Right. So let's now consider an interesting application of also an interesting application of the dominant convergence theorem. Remember that in many practical applications, we always wonder if we can we have integrals when we have derivatives. The question is if can we exchange the integral and the derivative, especially when there are more than one variable. When we apply the derivative to the integral, we will wonder if we can exchange the integral and the derivative, and that in that case probably become a partial derivative. And the answer is yes, provided that if we have some control on the partial derivative. Okay, result is given by the following theorem. So suppose we have a function f. For simplicity, we just consider the function to have two variables. Sorry, one is x and the other one is y, and it is integrable for in the x direction and differentiable in the y direction. So we'll see that soon later. So suppose we have such kind of function f, and that is defined for every x and y, and the x belongs to this measurable set E, and the y belongs to this interval AB, and it maps this pair x and y to a real number. Okay, now the f for every fixed y, the function like this is integrable on E. Okay, so when I write this, this means that the y is fixed, and then we can treat this as a function of x. And it's measurable, it's integrable over E for every y in the interval AB. And also for every fixed x, this function that is a function of y now for fixed x is differentiable on this interval AB for every x belongs to E. Okay, so these two conditions just guarantee that the integral that we're going to write out is well defined. Okay, so they didn't touch the core yet. So when we are trying to exchange the integral and the partial derivatives, we actually at least need to make sure that in either way it is well defined. This is just that. And the next, which is the key to dominate the convergence, is that if there exists a function a function g defined over E and is integrable over E, such that the partial derivative of f with respect to y, for any y, this one is bounded by the gx. Okay, I can just assume that gx is positive, non-negative, so I can just ignore this absolute value. So because this is the one that I'm going to dominate the integral, so I assume it is non-negative for any pair x and y belonging to the set. Then for any y, we can show that the following identity holds. So the identity is that if we consider to take an integral of the f for the E, then apparently this becomes a function of y. Okay, and then when we treat it as a function of y, we can consider derivative with respect to y, and we show that this actually is differentiable with respect to y, and the derivative of this is the same as you exchange the integral and the derivative, and you can apply the derivative inside to the integrand, but we need to use partial derivatives now because we need to specify the derivative is with respect to y only. Okay, so it's a partial derivative with respect to y of fx, y, and the method. Okay, so here's the proof. So now this is what I just mentioned. We can exchange the integral and the derivative. Okay, so the common way to prove this is to consider the limiting behavior of the what we call it, the secant, because the derivative is actually like the tangent, slope of the tangent. But we consider the slope of the secant line and see if they converge to the slope of the tangent line. So to this end, what we can do is to assume, suppose we have a sequence of numbers ek when let it go to 0. Okay, it could be positive, negative, but it's just a sequence of numbers that goes to 0, and define. We call this f k of x. Should be f of k of x and y, and that is defined to be the derivative is only along the y direction. So that's f of x y plus ek minus f of x y divided by ek. Okay, so this is like the slope of the secant line for every x and y. For every x and y belongs to the set E and the interval AB. Okay, and now because for every fixed x, this is a differentiable function. It's a differentiable function with respect to y because both of these two terms for fixed x, both of these two are functions of y, and it's differentiable. That means both of them are differentiable. So the difference of them are differentiable, and over ek is still differentiable. Okay, so for every fixed x, the fkxy is differentiable with respect to y. Okay, it's differentiable. And actually, what we really need is that when we fix the x, we can see this by mean value theorem. We can see that this ratio is actually equal to the partial derivative of f at some point between the y and the y plus ek. Okay, so this is actually one of the Taylor theorem you probably have already seen. That this is always for fixed x, consider this as a function of y. Then we can take a Taylor expansion of that, and that will be equal partial y f of x, and then this is some ck, where the ck is between y and the y plus ek. Right? So you know this. And that's why what we can claim that the fkxy actually is equal to the partial derivative of f with respect to y evaluated at this point. Okay, so we just continue with that. So the fkxy can be shown to be equal to f partial derivative of f with respect to y, and it's evaluated at x and the ck. Okay, and now we can take absolute value of that. So I just directly take an absolute value. It will be just divided from the equality. It will be this, and then because that we showed for any y, doesn't matter what y is, this one is bounded by gx. So this means this is bounded by gx. Okay, and this means that we can, since this is it's dominated by that, and we have the fk, and for very fixed x, we can have the fk of x and y, and this means that when we take the partial derivative, we take the integral of this. We know that for the fk, they convert to how should I say that? So the fk converts to the partial derivative of f evaluated at x and y, right? For k goes to infinity, this converts to that. So since each of this fk is bounded by a integrable function, so we know that this converts to the integral of partial derivative of f x and y, and a d mu x. Then we take the integral here. Okay, we'll converge that. Okay, now let's look at what happens to the left-hand side. The left-hand side, according to our definition of the fk, this becomes the integral of this ratio divided by ek d mu x, and so what this complete statement says that the limit of this thing converge to this. Okay, and the limit of the left hand side which is this, should be y here. We know that the integral of that can be split and applied to the numerator individually, so that would be just equal to, so on the one side it is equal to the limit k goes to positive infinity, and then I have the integral of fx y plus ek minus integral of fxy divided by ek. Okay, and on the other hand, I know that this is going to convert to this thing, right? So I just write it there. Okay, so now I will just claim that this left-hand side, or this thing here, is just the derivative of the integral of fx and y. The reason is that this, as you can see, that this is just if you treat this as integral of this as a function of y, we said this integral is with respect to x, right? Forget that. D mu x. So this is the function of x. So if we call this as, for example, the h of y, and then this one here will just become the h of y plus ek. So this whole thing will be just the limit of h of y plus ek minus h of y divided by ek. And this just means that it is the derivative of f at y. And this is just the dy of hy, but hy, as we said, is defined to be the integral of f xy d mu x. Okay, so that shows that this one here is actually equal to this. Okay, because the left hand side, the limit here is just equal to that, and on the other hand, it is also equal to this. Okay, so now let's consider an example. Suppose I have a integrable function on the Rn, this is on R, and I will also have a series 1 over ak is finite, where each ak is positive for all the k. Okay, then let's show that the limit of f ak times x, which is ak times x, is equal to 0 almost everywhere. Okay, so apparently we have been familiar with this. For such kind of f, which is defined or fkx to be the f of akx. Okay, and now let's see the let's consider the series of the integrals of fk. So consider the integral series of integrals. So it's k from 1 to positive infinity integral of this fk. So apparently this is just equal to as we defined, it's just equal to that dx, right? And then we can do a change of variable. Just inside, we're doing everything for each term in this sum. So do a change of variable. This becomes the f of ak x divided by ak. I can take f's value, then dakx. Okay, now the change of variable is applied to this akx. I call it, for example, I call it u again. Then it will just become f of u divided by ak du. We can apply absolute value. We don't need that absolute value for the denominator since it's positive. Okay, so now I have this. Where this ak can be pulled out because it's constant. And then this integral is just for f. It doesn't depend on k at all. So this part, as I said, this part is a constant for each term in the sum. But this is a finite number. It's a finite constant since f is integrable. So that's why this whole thing is finite because it's a finite number constant which when I pull it out, and the series here is finite because of that. So both are finite, just so that it's finite. And this is finite, we can use which of the theorem we just mentioned. When we take the infinite sum here, we can show that this limit is just the integral of the infinite sum. It's just the corollary above the previous theorem. Right? It's just equal to that because this is finite. Okay, and that means this thing here is integrable. So that means this is integrable. Okay, it's integrable means that it's finite almost everywhere. Okay, it's finite almost everywhere. And also this means that it converges to the fk itself converges to 0 almost everywhere. Okay, so I'm not really rigorous here, but I can. So we know that this is a finite. So this is the finite, and this therefore almost everywhere, and this means that the fk converges to 0 almost everywhere. Okay, and this definitely applies to fk itself converges to 0 almost everywhere. All right. Now again, so suppose that we have a integrable function. Then for any epsilon, positive epsilon, there exists a continuous function g. And most importantly, it has a compact support such that the integral of their difference is less than epsilon. Okay, so what this means is if you have an integrable function f, then you must be able to find a continuous function with a compact support so that this g can be arbitrarily close to f. Okay, so for any epsilon, that means for any epsilon, you can find such a g, and the integral, the g is continuous with compact support, and this integral here is less epsilon. So this can be this is a very useful result that we're going to use it for many times later. Okay, so let's see how to prove this. First of all, for any epsilon, we know that there exists a compact set k such that the integral of f outside of this k must be bounded, must be arbitrarily small. That means say for this epsilon, we choose it to be epsilon or 4. Okay? The reason for this, we have shown this before. The reason for this is that you can imagine, for example, in this case, when let's say just consider the most general case where the f is defined over the entire R. Because f is integrable, so that means this is a finite. Okay, and this can be also considered as the limit of the bk, where bk is the ball with centered at 0 with the radius k. We can consider this. Then since bk goes to the entire set Rn, as k goes to infinity, so we know that this one is growing, monotonely increasing to the integral of f over the entire set Rn. Okay, and they're all finite. Apparently, they're all finite. Okay, and then we can take the difference. Sorry. We can take the difference of the two. So the integral of Rn minus bk of f. So this should be going to 0. Okay, and that means for k large enough, this one will be less than epsilon or 4. And I just choose my compact set k to be this bk. Okay, so that's the reason. So you should be very familiar with this now. And now let's continue with this setup. So outside of the compact set k, the function has an integral bounded by epsilon over 4. And within the set k, there exists a simple function I call it h tilde, which has the support inside the k, such that the integral of f minus h on this k is bounded by, say again, epsilon over 4. And this is because that we, by definition of measurable, by the definition of integral of measurable functions, we can use where it's taken as the supremum of the integral of the simple functions, where the simple functions are bounded about by the function f, right? So we can just choose such a function, a simple function h tilde, so that it's close to the integral of f, which is the supremum of the integral of the simple functions. Right? You can do this. Just recall the definition for the integral of functions. All right. And apparently that we define that for non-negative functions, but for general functions, we can do the positive part and negative part easily. So that's not an issue at all. We still have this result. All right. So now we have this simple function defined over k only, but actually we also need to concern about what happens outside. But this just set h to be 0. So we can set the h the h defined over the whole set to be the, say, h tilde times c of k. It just means that within the k I take the value h tilde, and outside of that the set k I just take 0. So this h is a simple function defined on the entire E. Okay. Then we can see that the integral of f minus h over the set E, as we said, it can be partitioned into two parts. Either is in k or it is outside of k. If it's outside of k, the h takes the value 0, so we only have the f. If it's inside the k, you know that we have f minus h tilde. And both of them are less than epsilon over 4, so the sum of them must be less than epsilon over 2. Okay, so that's one part. And then we can focus on this h or h tilde because it's on a compact support, it's simple, so we can use the Luthin's theorem. So by Luthin's theorem, there exists a set f that is a subset of k, and the function continuous function g defined on with support also inside the k, such that well, I should say that for the delta to be the measure epsilon over 4m. Okay, so for epsilon, for delta to be epsilon over 4m, we know that there exists a set f. Actually, it's closed set of f, but we don't close set f, but we don't really need to close the part. So there exists f. That's a subset of k, and the difference of the f and k, the difference of the alpha k, we know that it's going to be less than delta, which is epsilon over 4m. Okay, this is one thing. The other thing is that outside the inside, so the f is almost as large as k. The difference of them is really small, and also over the f, the function g is identical to the continuous function h, and this is what the Lewis theorem says, that it is if the function h is measurable, then it is continuous. It's almost continuous, means that except for a very small set, the function h is continuous. And we just see that the continuous part matches the continuous function g. And outside of that, it can be anything, but g is going to be identical to the h. So what this m came from, m is the maximum value of the h. So the m so it's not assumed, actually it must be the case, because h is a simple function. So let m greater than 0 such that the h is bounded by m. Okay, I'm going to use this to get this delta. Then we choose this delta to be epsilon over 4m, where the m is the bound for the simple function h. And then there, by doing this theorem, there exists a set f that is a subset of k, and there exists a continuous function g with a support inside k, such that the measure of the k minus f is less than delta, and also the function h restricted to f is equal to g restricted to f. And also the g is defined continuously, and it can be extended continuously outside of the f. So the m is also applied to g. So the g is also bounded by the m. Okay, that's something we showed before. So with this, what we can claim is now we already have this part, and the part need to show that this we just need to show the difference between h and g. Now the difference between h and g, we know that they are identical on f, right? So what happens is only outside of f, so it should be equal to the integral of these two outside of f. Okay, and because h and g, they are both bounded by m, so it's bounded by 2m times the measure of e minus f. Okay, I should actually say that because the h and the g are both supported on k, so I should say that this integral of them on e is actually the same as their integral on k. Let me just put it here. And this is equal to the integral of h minus g on e, since they are both supported on k only. Okay, so outside of k is 0. And inside the k, we separate it into two parts. One part is f, and the other part is k minus f. But on f, they're identical. So it's only this part left. And then this is 2m times the measure of k minus f. So this should be k minus f. And we know that we got this f such that it's almost as large as k. The difference of these two is less than delta, which is epsilon over 4m. So I just need to multiply 2m times epsilon over 4m. And that's giving me epsilon over 2. And now we have both, right? I just apply the triangle inequality. Minus g over e is smaller than equal to the f minus h over e plus the integral of h minus g over e. And for both of them, it's less than half epsilon, as one is here. One is here. The other one is here. Okay, so that's how we got the epsilon. So recall this theorem as we said. For any integrable function, we can find a continuous function with compact support such that it can be close to the integral of the difference is arbitrarily small. Okay, or we can find some continuous function that this one holds. Okay, we're going to see the application of this in the later examples. Okay, so now let's consider a corollary of that. Suppose we have a function that is integrable. Okay, and then there exists a sequence of continuous functions with compact support or bounded support. You know, they're the same thing when we see the bounded support, because support is always we always consider support to be closed. So it's closed and bounded, then it should be compact. So there exists a sequence of continuous functions. Say we call them GK. Each of them has a compact support. So each of them has a compact support, but their support could be different as k changes, such that the integral of gk minus f goes to 0 as k goes to infinity. And also the gk convert to f almost everywhere. Okay, so the corollary is also very important. Suppose we have an integrable function f, then we can find a sequence of continuous functions with compact supports, such that the sequence of continuous functions convert to f almost everywhere. Okay, and also this integral of their difference is converged to 0. Okay, remember that this f is just integrable, so it's a measurable function. It could be really, really strange, but now we show that we can find a sequence of continuous functions, and they're actually with compact support, so that they convert to f almost everywhere, and also we have this integral. It can be approximate. The integral of f can be approximated by the integral of gk as well. Right? So the proof is pretty simple based on the theorem above. The first one is that we can directly apply the theorem above, because that for every, say for example, for any k, we can show that there exists continuous function gk with compact support such that the gk minus f is less than 1 over k, for example. Then apparently the sequence gk, the integral of the gk minus f will convert to 0. So the integral of gk minus f will convert to 0 as k goes to infinity, right? And based on this, we can show that the gk minus f actually gk actually converts to f almost in measure. The reason is we probably have showed this before. We showed this before. This if this integral goes to 0, that means that the gk converts to f in measure, and it's pretty easy because we can just define the ek. If you forget, we can define for every epsilon, we can define the ek to be the set of points where gk and f is greater, difference of them is greater than the epsilon, and then we can see that the integral of gk minus f on the one side it is bigger than the integral of that over ek epsilon g minus gk minus f. Okay, and we know that over this set, this integral is greater than or equal to epsilon. So it's bigger than or equal to epsilon times the measure of ek epsilon. And on the other side, I know this is going to 0 as k goes to infinity. Okay, and for the fixed epsilon, I know this goes to 0. That just means that this thing goes to 0 as k goes to infinity, and that means the gk goes to f in measure. Okay, and because of that, we know by the Reed's theorem, there exists a subsequence called gk. We can still call it gk. Let's call it gkj, and that will convert to f almost everywhere. And because this gkj is just a subsequence of the original sequence, so I still have this gkj minus f. This goes to 0, right? And we just use this subsequence as my sequence, and we can see that every one of them is continuous with compact support, and we have this goes to 0, and at the same time also this gk goes to f almost everywhere. Okay, so that's the proof. So now let's look at an example. Suppose I have a integrable function, and that the integral of f and phi is 0 for any continuous function with a compact support phi. For any continuous function phi with compact support. Okay, and that means the phi has a support with it has a bounded support, and it's continuous, and it makes this integral equal to 0 for any of such continuous function. Then this implies the f must be equal to 0 almost everywhere. Okay, this is used probably most of the case is used in partial differential equations or calculus of variation. The phi is considered as the test function. It's continuous and is used to test where the function f is non-zero. But if you try different types of phi, and it's always 0, that just means the f itself is 0, or it's 0 almost everywhere. Okay, so that's the application of that. Okay, would be very useful in partial differential equations. Okay, the proof is like this. Suppose not. Then we know that f is not 0 almost everywhere. Then that means the measure where f is different from 0 is positive. Okay, but this set here can be partitioned to two parts. One part is f is greater than 0, and the other part is f is less than 0. And these two sets are do not overlap. So that means at least one of these two sets has a positive measure. Okay, and without loss of generality, let's just say that the first one has a positive measure. Okay, and because the f greater than 0 can be considered as the union of f greater than 1 over k, right? Or greater than or equal to 1 over k. And because of this, we can see that we know the measure of this left set is equal to the measure of the union of these sets, and the right hand side is bounded by, because of the subadditivity of measures, we don't know if these sets overlap or not, so we only have the sub less than or equal to these sets, and that's what happens on this side. And on the left hand side, we know this is a positive measure, so it's greater than 0. Okay, so what this shows us is that for some k, this measure is non-zero, because otherwise, if every one of them is 0, then the infinite sum of them is still 0. The countable sum of them is still 0. Okay, that's a contradiction to that. This is the greater than 0. So that means such that the measure of f greater than or equal to 1 over k, this must be positive. Okay, so because of this, let the set ek to be this set. Then consider the measurable function, which is the characteristic function of the set ek. There exists a sequence. Apparently, this is the integrable, right? We take the integral of that. There exists a sequence gk continues with compact support such that the gk converts to this almost everywhere, and the integral of gk gk minus kce is going to 0. Kek is going to 0. So I should no, I should not mix the k, but here, since we already fixed the k, let's just call it e. Okay, for this k, we'll call it e, and then I will have the e here, also the e here, and we're going to use the gj instead of gk. Okay, so that is ce, and here the gj with compact support such that gj converts to kce, and the gj minus kce as this integral goes to 0. Okay, and now you can see that the function f times gj, maybe I should call it phi j, since I used the continuous function phi earlier. Let me use the phi j. The phi j, this phi j goes to kce, and this phi j goes to kce. So here I will have the f times phi j. Okay, I know that this one will have will convert to, will be bounded by this kce, and that is bounded by the f itself, and that is integrable. Okay, we approximate this kce from below. That's always okay. right? Because we can consider this this K is the one divided over the set E, and this continuous function is approximating the K from below. And you can see that from the original the proof, we actually considered a function, a simple function below the original function f, but that function is K here. The f function is K here. We consider a simple function that is always less than or equal to that, and this continuous function is less than or equal to the the simple function even. So that's why the continuous function we constructed can be always bounded above by that function. So that's why with the phi j, it's actually going to K from below. So I can really actually write in this way. Okay, we'll have this. So that's this first part is because the phi j is approaching to K from below, and this part just because the K is equal to 1, is bounded by 1. That's why we have this, and this is the integrable function. So that's why we show that this is the case. Okay, and now let's consider the integral of f on K, and because that each of this is dominated by this, so we can use the dominant convergence theorem. We know that the limit of this has the integral equal to the limit of the integral. Okay, so when we take the limit of this phi j, limit j goes to positive infinity, is equal to I take the integral of the limit. The limit can be exchanged with this integral. And when we exchange that, this limit of the integrand is just the f K. Okay, so this just means that the integral of this is equal to the integral of this by dominant convergence theorem, because each one of this is bounded by the f. Okay, so that's why we get this inequality. And on the one side, this is greater than or equal to the 1 over k times the mu of e, because we know that on this set e, the function f takes the value 1 over is bigger than or equal to 1 over k. Okay, and apparently because the measure of e is positive, as we said, this is the e and the measure is positive, so this is the positive on the one side. The other side, let's look at the integral here, because the phi j is a continuous function with a compact support, and this f is this is just because this must be a compact support. This one has a measure. The mu of e must be finite as well, right? So otherwise, the integral will be the integral of f on over e will blow up, because the f is greater than or equal to 1 over k. And if this is the infinity, or this is infinity, then even this one will be infinite, right? So that's that contradicts to the fact that the f is integrable. Okay, so that's why this phi j here is continuous and with a compact support, and we know that for each of the such continuous function, the integral is equal to 1. So the limit of that is still equal to the integral of that is equal to 0. So the limit of that is still equal to 0. And then we have the 0 greater than 0, and that is a contradiction. And that means that initially we can not get this equal to greater than 0. It has to be equal to 0. Right? So that's the application of the theorem we just discussed. Okay, we can consider even similar, but slightly modified example. So suppose we have a function f that is integrable, say integrable over a closed interval AB only. So we're going to consider the derivative. Okay, so if the integral of f and phi prime is equal to 0 for any differentiable phi with support phi inside AB, then f will be equal to a constant almost everywhere. Okay, the constant is to be determined, but it will be some constant almost everywhere. Okay, for some constant c. Okay, so this is what we're trying to prove. Okay, to this end, let's say that for any continuous function g with support g in here, and also another continuous function h, also with support in here. But I have an extra condition. I want the integral of h to be equal to 1. Okay, so for any such kind of functions, I can define phi x to be the indefinite integral of g, let me use gt dt, minus the integral of ab of gt gt. So here, this one is a constant. The one in the parenthesis is a constant because I already fixed the end point to be b. And then also have a to x, ht dt. So these two are functions of x. So this one is a constant. Okay, so that's my function phi. And apparently it's a continuous function, and it's also differentiable because g and h are continuous functions. The indefinite integral of continuous functions are differentiable, and the derivative will be just equal to the g and h respectively. So this is the fundamental theorem of calculus. And now we know that the phi prime is just equal to the gx minus the constant that doesn't change, still the same constant, times hx. Okay. Now let's consider the integral of f and the phi prime. So that's equal to the integral of f, and the phi prime is equal to g minus the constant and also the h. Okay, so I can split them. So the first one is this, f and g. The second one is because this is a constant, I can pull it out. And also I have the integral of f and h. Okay, and what do we know about it? It's equal to 0. But before that, let me just do one more thing. This is equal to integral, because both of them have this f, and they have the g, and the other one has this h, but I have this constant multiplied to h. So it's actually, oh sorry, I can pull out the g instead of f. So, yeah, so this is a constant, which way I'm going to put together. So this constant I'm going to put inside in front of g, and also have this f in front of g. So together, that would be just the f minus this constant ab fh integral of g dt. Okay, so we will get that. And as you can see, the G is continuous with the compact support here. So that's true for every such kind of G, and this one is equal to 0 because we know that this is equal to 0. So that just means that this part is equal to 0 almost everywhere. All right. Okay, so that's why the f should be equal to the integral of this fh, and this is a constant almost everywhere. Okay, because this integral does not depend on x at all; it's just a constant number, and this the constant f should be equal to. Okay. You may ask where we use the fact that the integral of h is equal to 1. We used it here. The reason is I need to make sure that when I integral up to b, this function, the value will vanish. So when this becomes the b, I will have the b here. But when this is the b, this should be equal to this. That means that the integral of this must be equal to 1. Just for this one, this should be equal to 1. Okay, then that's how these two cancels. And that's the phi of b will be equal to 0. Because the phi has a compact support inside the interval ab. Okay, so that's why this is the finally we get this f as a constant almost everywhere. Okay, so